Hey, going? Another torsion question. Okay, so knowing that each of the circular shafts AB, BC, and CD is hollow and has an inner diameter of 10 millimeters. So each one of these shafts here has an inner diameter. Determine A, the shaft in which the maximum shearing stress occurs, and B, the magnitude of that stress. Before we proceed, the formulas that we are going to use will be shearing stress equals to torque times radius divided by moment of inertia. And since we have an inner diameter and the shaft is not fully solid, the moment of inertia formula that we are going to use is pi on 2 bracket radius 2 to the power 4 minus radius 1 to the power 4. Now, so we're going to solve each one of these members individually. So I'm going to start from A and solve A to B. The torque will be we cut the shaft, and we'll define sum of moments. Positive is the clockwise direction, so we will have positive 90 Newton meters minus torque AB equals to 0. So that means torque AB will equal to 90 Newton meters. And then the moment of inertia will be for hollow shaft, so it will be pi on 2. Our radius will be half this diameter in meters. So if this diameter is 20 millimeters, it will equal to 0.02 meters, and half of that will be 0.01, which is the radius for this shaft. And then minus to the power 4, and then minus the internal radius, which is just half of that diameter in meters. And then we'll get this value. Now to find the shearing stress that this shaft, the max shearing stress that this shaft will experience, the shearing stress AB will be 90 times the radius 0.01 divided by that moment of inertia value, which will give us 6.11 gigapascals. Now, solving for B, it's very similar. So we imagine that this shaft keeps going, and then we cut it here, and we have the direction 90 there. 270 is an anti-clockwise direction, and then we're gonna follow the same direction we started with that initial torque, which will be anti-clockwise. So it will be positive 90, negative 270, and negative torque BC equals 0. Now you'll find here that torque BC equals to negative 180. Don't fret about that. That just simply means that the initial direction we assumed is actually is wrong. So that arrow should point into the clockwise direction, and so we will not include that negative in the final calculations. And then moment of inertia will be half of that diameter in meters, which is 0.0125 to the power 4, minus half of that diameter in meters, 0.005 to the power 4, multiplied by pi on 2, given that value. And then torque BC will equal to 180 times 0.0125 divided by that value for moment of inertia, giving us 6.02 GPa. Next and last one, we'll be solving for CD, and so we will following the shaft, and then we cut it between C and D. Then we will apply the torques as shown, and then following the original direction we started here, we will draw torque CD in the negative direction. So then we go positive 90, negative 270, negative 110, negative torque CD equals 0. And that will equate to torque CD equals to negative 290. So that just saying as before that our assumed direction is wrong. We would just, the torque would be acting in the other direction. And we will not be including that negative in our final calculation. And then we have the moment of inertia, which is pi on 2, half of that diameter in meters, to the power 4 minus half of that diameter in meters to the power 4 will give us that value for the moment of inertia. And then the shearing stress for CD will equal to 290 times 0.015 divided by that value for moment of inertia, which will give us 5.54 GPa. Now, have we answered our question here? Well, we did indeed answer B, the magnitude of that stress. So we have the magnitudes of all the stresses, and in the shaft of which the maximum shearing stress can occur will be shaft AB. However, and that value is 6.11. However, in the grand scheme of things, if that shaft is being loaded with that much shearing stress, shaft CD will snap beforehand and it'll probably never make it to that value. Anyway, thank you.